what is going to be the value of S3? The confining pressure, right? Notice that the way that we apply S3 is through this membrane and is controlled by this pump. And we apply with pressure. But when it goes through the membrane, it transforms into a stress. The value of S1, sometimes, and this is what you're going to do in the lab, so when you go to your lab, S1 is going to be measured directly. In the lab, you have something on top of this which is called a load cell, which is going to give you a force, and you divide the force by the area of this plunger, of this piston, and that's going to give you exactly the value of S1. Otherwise, what you can do, and this is what you have in your assignments, and what I have also in my laboratory, is you use a load cell that tells you the value of the deviatoric stress, defined as S1 minus S3, which is also equal to sigma 1 minus sigma 3. What is this deviatoric stress? Deviatoric stress is the difference between S1 and S2, and in this case, if I put a load cell, it's going to be this element over here. So inside here, let me draw this a little bit different. If you have a load cell, notice that the load cell is going also to feel the pore pressure or the confining pressure all around the sample. And if you didn't have any stress in this direction, it wouldn't feel anything. It would just feel the confining pressure. But if you have an additional stress, the load cell is going to measure that. So that load cell is going to give you the difference between the maximum principal stress and the minimum principal stress, and if there is any additional stress in another direction. And once you have all those values for different tests, for different samples, you can plot what the results of those are at different values of confinement, and then the line that joins that is going to tell you what is your equation of sigma 1 at failure, which, if this is a line, is going to depend on two constants. The intercept is going to be the unconfined compression strength, and the slope is going to be this parameter Q times sigma 3. And that's all you have to know for now about the triaxial test. Yes, A1.
So wouldn't the sigma 3 just remain constant just because it's pore pressure? Would we be changing that?
Very well. I forgot about that concept. In all these kind of tests, in a triaxial test, confining pressure remains constant during the test. And it remains constant so that, for example, when you start the test will usually start somewhere over here. And as you keep on increasing the axial stress, this will go up, 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 and it will fail at that point. If you were to increase the confining stress and start over here with another sample, sigma 1 will go up, 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 till it touches that line and it fails. But that one always remains constant. From this kind of test, it's also exactly the same as the unconfined compression test. You can also measure what is the change of length in this direction, and you can also measure what is the change of length in that direction, and that allows you to measure also Young modulus and Poisson ratio. It happens that as you increase the confining stress, as you may imagine, the rock gets stiffer. And as it gets stiffer, Also, your Young modulus and your Poisson ratio are going to be different than the ones that you measure in non-confined conditions. Yes, Ms. Montero.
So when finding Q, do you recommend getting the slope of the line or finding the slope? Because I know in your previous exams you posted, you had like a table.
Okay, so if you were doing it numerically and very accurately, I would recommend to go this way as you did in homework.
The slope?
Just draw a line. If you're doing it in the test, just draw a line as I did here and tell me what is the intercept and what is that slope, and that's it. That's everything I want. Any question about the triaxial test? Yes?
So triaxial, there's stress applied in all three directions?
Very well. I forgot about that too. This is called triaxial test because this is a cylindrical sample, and if I draw it in 3 dimensions, I'm going to have S1 apply on this face. Usually I just draw S3 on this direction, but all around the rock there is going to be stress as well. So the intermediate principal stress or the stress perpendicular to this direction, S2, is just going to be equal to S3. So because of that, in these kind of cylindrical axisymmetric tests, we don't talk about S2, we just talk about S3 because S2 is equal to S3. And that also brings a very good point, because in reality and most applications, this is not what happens. You usually have stresses which are actually different in 3 directions. And that requires a little bit of a modification of some of the equations that we use in order to predict failure, for example, around wellbores. All right, if you don't have other questions, I'd like to move to the solution of the homework. And then if you have some questions about the exams, I have the exams with me, we can talk about that, okay? All right, so let me find the solution of homework number 3. And I also have homework number 1, number 2, if you have any question, okay? All right, so this is the solution over here. This thing is the same thing I just drew before. And the first point here is just to make sense out of this table. Here, usually, this is what you set, confining pressure. You can also set pore pressure, and this is what you measure. With this, all these quantities, what you have to do is to compute the effective stresses. Once you put all those effective stresses, you plot them as sigma 1 as a function of sigma 3. You throw a line through that. If you're doing this with Excel, use a regression. If you're doing this in exam, just get a ruler, draw a line, just eyeballing what you think is the best fit, find the intercept, calculate the slope to your best of your abilities, but you don't have to run a regression line in paper, okay? Don't worry about that. Just tell me more or less what is the slope, and from here you're gonna be able to get your equation for the failure line, which is going to be, in this case, 100 MPa plus 3.2 times sigma 3. And that's everything that you have to do. Conceptually, what does this line mean? Well, it tells you the strength of the rock. The lower the line, the less cementation it has. The steeper the line, the more frictional strength it has. So this is a weak rock, uncemented rock, and as you increase in this direction, it gets stronger. more circles. If you have to draw the more circles for that, if you're doing this in paper, the only thing you have to do, and always draw effective stress more circles, okay? I'm not a big fan of total stress more circles. So draw effective stress more circles, you find the principal stresses, and then you just throw a circle in between. If you're doing this with Excel, it may take a little bit of time. I recommend that you have at least 50 points around here, so you have to create a table, and you will have to use the equations that we discussed over here. So you create a table as a function of the angle, and you throw 50 points, and you plot those as a dispersion plot, and you will get your circle. If you are doing this with MATLAB, I don't remember seeing a function for drawing a circle in MATLAB. So you will have to do something similar to create a function that as a function of an angle calculates 100 points, and then you plot that, and then you get your circle. You get all your circles, and then you plot this line. How I got this line? I didn't get this line to fit a tangent to the circles, because that takes a lot of work. And instead what I did is, using those parameters, UCS and Q, I used the equations that are in the class notes, and you have them also over here. From here, I can calculate what is the friction angle. If I know the friction angle, I can compute what is the, if I compute the friction coefficient, I can compute the friction angle. And if I know what is UCS and what is Q, or the friction angle, I can compute what is the cohesive strength. The cohesive strength is the intercept of this line in a tau sigma m plot, and the friction coefficient is the tangent of the friction angle of this line. Let me write that a little bit better. Similar to what we discussed before, in this type of plots, a line that goes through the original coordinates, it means an uncemented rock, and it goes up and steeper, it gets stronger and stronger. Any question about this problem? Yes?
So if you were to do it in the exam, with the line, so if you don't have like 3 or 4 or more circles, would the line have to be tangent to all of them, or is it okay if it doesn't touch some of them?
So it will have to be,
I mean, even in the diagram, it wasn't touching all of them.
so there is one exam like that, right? There is one exam in which you have to do that. I will draw the circles and then draw to the best of your abilities a line that is more or less tangent to those. And from there you can get the cohesive strength and you can get the friction angle. It doesn't have to be perfect, okay? Don't worry about that. But the concept is that the line has to be more or less tangent. That's it. So here I have put a summary of, let's see if it's here. No. Of, you see, different kind of rocks. So usually this is what we discussed before. The higher you go in this axis, the stronger the rock is, the more cemented it is, and the steeper the line, the more frictional strength it has. So for example, here in red you have igneous rocks. This is the rock that may be in your kitchen, right, for the countertop, granite. Here we have a metamorphic rock in green, and all of the rest are sedimentary rocks, usually weaker than the igneous rocks and metamorphic rock, depending on which rock you're talking about. But probably, you know, when you think about the rock, you have an idea about a granite. Very strong, very stiff. The rocks we deal with in petroleum engineering, they can be very well cemented, usually less than those, and can go all the way to 0 if you have an uncemented sand, or an uncemented silt, or an uncemented mud rock. Yes?
So just to repeat, the y-axis, the y-intercept determines how well cemented it is, and
Yeah.
the slope determines how strong the material is.
What is the frictional strength? The frictional strength. Some of these rocks, you see, they have a very steep line, and that also means it's a little bit more about friction. It's about they have a granularity inside. Like if you think about granite that has crystal grains, those, in order to go on top of each other, there's more than friction. There is also dilation that makes that apparent friction coefficient to be bigger than the typical friction coefficients that we deal with. All right, so let me come back to the homework. Failure plane is going to be simply 45 degrees plus the friction angle divided by 2. And remember, it is always a steep angle from the plane in which you apply the maximum principal stress, which in this case is a horizontal plane, and that's the angle. Pore pressure. Pore pressure. Pore pressure doesn't affect the shear strength of the rock. It just changes the effective stresses. If you were to plot, let me see if I can get this into. I'm going to connect to my computer, and I think in my computer I have the exam open. So close your eyes, okay? I'll try to move quickly out of it. Let's see. Okay, so this is the same problem. This is the table, okay? So sigma 3, sigma 1, and then you plot those sigma 1 and sigma 3. What I have done in this plot is to plot sigma 1 and sigma 3, but color-coded with pore pressure. So all of these points are triaxial tests that are done with a different pore pressure. And if you look, for example, at those 3 points over there, they are almost exactly in the same location, but they were done with 8 megapascals, with 55 megapascal, and with 96 megapascal of pore pressure. Quite different pore pressure. But when you calculate effective stresses, if they are about the same, they fail at about the same point. So pore pressure doesn't really have an effect on the shear strength. It has an effect on many other things, but not that much on the shear strength. So the answer to that point is that no, there is no effect of pore pressure on shear strength. And the next point is with the triaxial test to compute Young modulus and to compute Poisson ratio, and also to look at volumetric strain. So let's see what is going on. I gave you data for a real test that we did in the lab, in which in addition to sigma 1 or to S1 and S3, we measured the shortening of the sample and the widening of the sample, right? So if you were to plot that, and this is what you will see as a function of time. This is what the load cell measured. This is the deviatoric stress. And this was done at a confining pressure of 1500 psi. So at the very beginning, there is no deviatoric stress. You apply deviatoric stress, the rock starts to deform, and this is the imposed axial strain. Many of these tests, the way that we run them, and this is the same that you're going to do in the lab, is you fix a strain rate. In this example was a strain rate of 4 to 10 to the minus 6 per second, which for this test we required about 1 hour in order to run the test. So this is how slow it was. But something very important for you to remember is that in many of these tests, you set what is the strain rate or the displacement rate, and you measure the stress. Let me continue with this. If this is just a calculation of the strain rate with the linear regression. Now, if we plot, we get rid of time, we plot deviatoric stress as a function of axial strain, and you get this curve. So this is the loading going up. This is the unloading going down. If you let me come back to the previous plots. As function of time, you see this is loading, this is unloading. Why do we do that? We do that because rocks tend to develop plastic strains. That's something that we're going to talk about on Tuesday. That is the only part missing about elasticity and behavior of rocks, strain behavior rocks, that tend to have a lower Young modulus in loading than in unloading. That's something called plastic strain. It's also related to viscoelasticity. But we usually do these unloading cycles when we test these samples. And from this curve, you can do a curve fitting of sections of that curve. And from here, for example, at 25% of loading, if you were to calculate the slope of this line, you will get the Young modulus about 3.3 million psi. Did you guys get that? Yeah? Mr. Boswell, you got that number? Yeah? What about the unloading? 5 and 7. Yeah, I think, if you look here, so I think this one is 5, this one was about 8. So the unloading, you will do it by fitting the lines to the unloading part. And the last point, well, not the last one, but number C was to compute the Poisson ratio. The Poisson ratio is going to be the ratio of the radial strain to the axial stress. So if you compute the slope, let me do it on the other side. If you compute the slope of this line, this is going to be the Poisson ratio. And notice that it's a negative value. So the negative value of that is going to be the Poisson ratio. So in this case is at 0.5 was 0.37, but if you calculate that at 25%, it gives you the value of 22%. Did you guys get that value?
Yep, 0.21.
It's the same, don't worry, okay? So and how many points did you take?
I did it a little bit higher up, and when I did
Okay.
more points you take, the bigger it got. So I did
Okay.
maybe like 40 points or 30 points.
Okay. Okay, that's okay. And if you were to plot the axial strain and the radial strain together as a function of the deviatoric stress, you'll find something like this. This is just the definition of the Poisson ratio. Next, you had to compute the volumetric strain. And the volumetric strain is the result of adding all the strains, right? And if you were to compute in a triaxial test, what is the strain tensor? Here you will have axial stress, here you have radial stress and radial stress. So the volumetric strain is going to be the summation of these three, which is this equation over here. When you plot the volumetric strain as a function of either the axial strain or as in this case, a deviatoric strain, you will see that in many of these triaxial tests, when you start compressing the sample, the volume of the rock actually gets smaller. So your volumetric strain is positive according to our convention. So contraction is positive for us, so that's why this one increases. But when you get close to failure, there is a phenomenon which is called dilation. And what that means is when the rock starts to fail, actually the volume starts to get larger. So why is this? The phenomenon is that, imagine that you have a sandstone, okay? And these are the grains of the sandstone. And it's very tightly packed. And at some point, the grains of those sandstones, as you apply shear, they start to move relative to each other. So now if I want, for example, this grain to move down, it will have to go to roll over and to move on top of that one. You see that? And when that happens, in order to accommodate that rolling over and grains going on top of each other, the sample is going to expand. So when you get close to failure, many rocks, not all of them, they start to dilate. And the volume starts to increase. And you capture that by plotting the volumetric strain. So all of this strength is contraction after a given point here. You have expansion. And that point over there, it's called the point of dilatancy. You can look at this a little bit differently. If you plot it as a function of deviatoric stress and volumetric strain this axis, you will see that all of this is contraction, compaction, and once you get to that point, you're starting to failure and you're starting to dilatancy. The last point was about to estimate UCS knowing what is the friction parameter. And for that, simply you have to use the equation of this line. You know what is this point, sigma 3, you know what is sigma 1, you know where that point is, you know what is the slope of that line. I'm just asking you to find that point over there. So that just comes from the equation sigma 1 equal to UCS plus sigma 3 times Q. All right, how are we doing with time? 15 minutes. Questions about the practice exams or about this, about the homeworks?
In this last question, the
Yeah.
last part, you just like go over it because it was the same case where like sigma 3 was constant at 1500 or something.
Yeah, I don't get how you can have a graph like that when sigma 3 is constant.
But then what I did was I took the peak stress and that's just how I calculated it. So I'm not sure.
Okay. This equation is for sigma 1, that's a failure value, and usually when you run this test, this is a constant for each test. So similar to what we did before, if you were to start the test, you will start somewhere over here. Actually, you will start a little bit, you'll start over there because sigma 1 has to be equal to sigma 3. And you increase till you get to the failure point. That's your failure point. The line, this is the failure line. So it's just an equation for those failure points. So is that clear or not? But probably it's not. What is causing confusion? So remember this is just the equation of a line, right? The equation of a line, and we know one point in the line, we know the slope, we know all the points, we know all the equations. So in this equation of a line, you know one point of the line and you know its slope. But that point of the line happens to be that point here where sigma 3 is equal to 0. But now you know a point for sigma 3 which is not equal to 0, and you know its slope, but it's still the same equation. So you know sigma 1, you know sigma 3, you know q, the only unknown is this one. Yes?
A question that's off topic, but is Hooke's law isotropic?
It's not necessarily, but in all our examples, we're going to assume isotropy. Any other questions about the homework? No? Shall we go through the exams very quickly? Okay. So in the exams, I'm going to give you at the beginning some conceptual questions. Okay. And for this, it's very important that you come to class, that you read the notes, and then you understand all the concepts, because this is going to be about 40% of the grade. Something else I'd like to tell you is that usually the first midterm is a midterm in which I get the best grade out of the 3 exams. The first midterm, second midterm, and the final exam. So you try to make your best in the first midterm because it's usually the easiest one, or the ones in which people usually get the highest grades. So I'm going to give you some conceptual questions. If there is something that here you don't understand about the wording of the question, just let me know. Okay, I'm going to be there. I'll be happy to discuss that with that, to clarify that. I'm not going to tell you the answer, of course, but I'm going to clarify that. But it's going to be mostly conceptual. Read the notes. You will see that everything is in there. Let's see this problem. It's a problem about computing bulk density. Not too difficult, right? So bulk density is a volume